So we're going to be taking a look at the optical elements that are at work inside of a telescope. Now the first thing we need to understand is that light from a distant star or object is going to be cast along a continuous beam or ray of light, and what we see is an infinite supply of photons coming at us from that source. Now when it hits an optical element such as a lens, that light is going to be bent, or what we call refracted. We'll learn a little bit more about this in grade 10. And as it's refracted, it will want to meet at a place known as the focus. So if we can have two beams of light for just a second here, we see that those two beams of light are trying to meet somewhere right about there. And as long as those two beams of light are coming from a distant source, they can be treated as parallel. So even though the two beams of light coming off a star are actually heading in slightly different directions, for our purposes, any two beams that make it all the way here to Earth, however many light years away we are from that star, might as well have been coming in parallel. And so, just like the two parallel beams from my lasers here, if I can get the angle right, okay, we see that those parallel beams are going to want to meet at that focus. Now, if I place another lens at that focus, I can straighten out that beam of light. Let me just turn the lights off here so we can see that a little bit better. I can straighten out that beam of light, and so it's going to come directly into my eye. So if I have an eyepiece here, I can be observing what is going on in that telescope, and I would actually be able to see the light from both of those rays refracted back. That's just scattering all over the place now. I'd actually be able to see the light from both of those rays refracted back into my eyepiece. And that's essentially how a refracting telescope works with lenses. Now, a reflecting telescope, on the other hand, works a little bit differently. What we have instead is a mirror that's going to reflect light back, and just as before, our two parallel rays should reflect back and meet right at this point right here, which is going to be our focal point. So those two reflected rays are going to meet right at that focal point right there. Okay? Now, if we wanted to redirect that light outside of my telescope, so you can imagine that we have the long tube of a telescope here, and we have to redirect that light out, we can take just a regular mirror and send that beam of light, it was working there we go, we can send that beam of light out the telescope through an eyepiece where you can be observing the image that you see coming from that light. And in that case, it would be a magnified image. Now, if we have a different mirror at the back of our telescope, so instead of this nice gently curved mirror here, if I had a mirror with a much more intense curve, we see that that is going to reflect that light back at an even steeper angle. Okay, so the properties of the mirror will determine how, at a less steep angle. So the properties of the mirror will determine whether that light comes straight back or whether we get a little bit more of a bend to it like we do with our deeply curved mirror right here. Okay, so those are the two things that are going to influence how that light comes back. The curve of the mirror and the material that we make the lens out of, as well as the curve of the lens. So the same material but a sharper curve gives me more refraction. The same material with a shallower curve gives me less refraction. In this case here, a shallow curve sends that light back pretty close to on itself. A deeper curve, and we have a little bit more reflection. We'll just end with the image that you can see there, the light coming back in and then hopefully being redirected to our eyepiece. If I were to put, where's my eyepiece? If I were to put my eyepiece back in there, you can see how that light would come out and be able to go to your eye. So we're going to do a little bit of a demonstration here on, oh, you can see my dog in the background there, on how a telescope gathers up light. So if we imagine that your eye, your pupil, really restricts the amount of photons that can come into it from a distant light source, the same way that this little container here really isn't able to gather up a whole lot of rainwater falling from the sky. But if we were to put a funnel on one of these containers, then it's going to gather up a little bit more of the rainwater that's falling down. So if we mimic the rainwater suddenly start falling here, I was waiting for the rain to come, but I thought that would be a pretty slow video. The telescope here, because it has a wider surface area, is able to gather up a lot more light. And even though the rainwater is a little bit closer, the rain's falling a little bit closer to the first cup here, it's going to take a little bit longer. Let me just get above here. It's going to take a little bit longer to fill up that first cup. So I'm trying to go down kind of right between the two here. We should be getting about an even spread of rainwater falling into both containers. Okay. And what we have to remember is that when you look through a telescope, you're seeing the light that's falling in that particular instant. And so if we imagine that 30 seconds of spraying there was the light falling in one instant, we see that this particular container here did not gather up very much light at all. But this container here, we've got quite a little bit of light gathered up into that container. Now, the beauty of modern photography, as of the discovery of Pluto, one of the reasons why we were able to finally discover Pluto is that modern telescopes are able to combine the light gathering ability of telescopes with the light permanency, if you will, or the light collecting ability of photography. So as early as the 1920s, when Clyde Tombaugh was studying and looking for the mysterious planet X at the Lowell Observatory in Flagstaff, Arizona, we were collecting and making permanent plates. So not just somebody's brief look at what the stars look like, but a permanent image of that area of the sky. And because of that, they were able to soak up light continuously for long periods of time. Now, there's all kinds of mechanical issues with that, in terms of you had to keep the telescope rotating at the same rate as the Earth was rotating on its axis. But once those problems were overcome, then we were able to start gathering up huge amounts of light and really being able to resolve very faint, very distant objects, which is what Clyde Tombaugh did in his discovery of Pluto. So you can imagine that over a longer period of time, you're able to gather up even more light. This one here still doesn't gather up very much at all, so we're going to move past that. But we were still limited in how long we were able to gather light for. Why? Because we could really only keep our telescopes aimed at a particular star or area of the sky over the course of the night. It wasn't until we were able to launch telescopes into orbit around the Earth that we were able to negate the constant return of daylight and basically having to stop photographing or stop gathering light from a particular object as soon as the sun came up in the morning, because the sky got too bright. So now, because we're able to have those telescopes constantly orbiting the Earth, they can remain pointed at one area of the sky, which is how we're able to get images of things like the Hubble Deep Field, where they basically take an exposure for like 3 days long, constantly aimed at the same area of the sky. And even though you might only be getting 1 or 2 photons of light hitting your telescope, per second from that particular area of the sky. Over the course of 3 days, you can gather up enough photons from that particular object or area of the sky or star or nebula, what galaxy, whatever it happens to be. You can gather up enough photons of light to really be able to resolve what that object is and start to see some detail, be able to detect color in that object. And even in the case of the Hubble Deep Field and the Hubble Ultra Deep Field, we can see objects that we did not even know there was anything there. Like, we were aiming the Hubble telescope at a black area of sky when they first resolved the images in the Hubble Deep Field and the Hubble Ultra Deep Field. So grade 9s, now that we've seen what some of the optical elements inside the telescope are, I thought we'd take a look at the outside of the telescope and see exactly how all those things fit together. So this is a reflecting telescope, so it's going to be based on the mirrors that we were looking at. The other type of telescope that you would see is a refracting telescope, in which light comes in from the front of the telescope here. It passes through a lens right away. That lens starts bending the light, and then you would look through an eyepiece back here at the back. But this one, as I mentioned, is a reflecting telescope. It's what's called a Newtonian reflector because it's based on the designs that were modified by Sir Isaac Newton and the type of telescope that he used, whereas Galileo used a refracting telescope much earlier. So if I adjust this, we should be able to see down into the deep end of the telescope here, and way back at the back end here where I'm standing is a mirror. This one's about 5.5 inches across, which gives us a nice gentle curve, and the focal point of that light, the same way that we just looked at in the lasers, the focal point of that light is way back up here, where we see inside the telescope right here. I don't know if you can see it, but there's a little central area here that has another mirror built in, and that reflects the light back out here through the eyepiece. Now, you're probably wondering what this last little device is here on the telescope. A lot of telescopes will have a smaller scope that sits on top. It's what's called a finder scope. This does pretty much the same job. The job of the finder scope is to provide you with essentially a non or a slightly magnified view of the sky, and then there's usually a little crosshair or a bullseye inside in which you can view and place what you want to look at dead on the center there, because frankly, once we start magnifying the sky, we're really looking at less than half a degree. So if you were to hold your baby finger up again, that's about half a degree. So if you hold your baby finger up and cover something in the sky, that's really what you're looking at through the telescope. So you can imagine that if you start looking through the telescope and you're just wandering around aiming that telescope around, you don't know if you're looking at what's supposed to be a black area or whatever. You think you're looking at one star, you're really looking at a different star. But looking through the finder scope here, because it doesn't really magnify the sky very much, if at all, that allows me to look at it and compare where the orientation of different objects are and say, this is really what I want to look at. It's dead center. This one here actually does not magnify at all. It's what's called a telrad, and it projects a bullseye with a little laser. So the little laser shoots up here and projects a bullseye on this screen. I don't know if you can see the screen. So right on that screen there, it projects a bullseye, and I look through here, and that bullseye is projected against the sky of whatever it is that I want to look at. So that's a quick look at our telescopes, and basically how a regular Newtonian reflector would work.
So we're here at the Lowell Observatory. The curators have a couple of telescopes out for us in the optimism that this stuff is going to go away, and this stuff is going to go away, and we're going to get to see some stars and nebula and a couple of planets later tonight. So this is a 16-inch Newtonian reflector. Most of you from class probably recognize the telrad that they've got on top as their star spotter or their finder scope, and then we've got the eyepiece all set up here. This uses a black cloth over the base, like the large Clark telescope that we were showing a minute ago. It's completely unenclosed, So they just put a black cloth over the base. Really, that's all you need, because you got your mirror at the bottom and your mirror at the top, right behind that eyepiece that the curator's installing right now.